two projects. In this video, we are going to explain the project Graph Neural Network for Air Quality Prediction, a case study in Madrid. Introduction. This project focuses on spatiotemporal prediction of nitrogen dioxide NO2 concentrations in Madrid utilizing air quality, meteorological, and traffic data. Employing advanced techniques, particularly the Attention Temporal Graph Convolutional Network, that is A3TGCN, the project aims to enhance the accuracy of predictions compared to previous methods. Air pollution stands as a significant global risk to human health, impacting a considerable portion of the world's population. Its consequences contribute significantly to global mortality rates. A substantial majority residing in areas surpassing air pollution thresholds faces health risks. This underscores the urgency of monitoring and enhancing air quality. So, the project aims to tackle these critical challenges by offering insights derived from advanced spatiotemporal prediction models. And the significance of the project lies in its potential to offer decision makers advanced knowledge of air quality concentrations. By predicting nitrogen dioxide levels with a spatiotemporal approach, the project contributes to effective pollution control measures. Beneficiaries include government bodies, environmental agencies, and the general public, ensuring improved health outcomes and ecosystem preservation. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to develop effective tools for air quality monitoring, modeling, and forecasting, recognizing the pressing challenges faced by citizens, decision makers, and governments. We aim to utilize advanced machine learning and deep learning methods to enhance accuracy in capturing and processing multidimensional information and complex dependencies, outperforming traditional domain knowledge methods. The goal is to introduce an attention temporal graph convolutional network combining attention, a gated recurrent unit, and a graph convolutional network, and we focus on leveraging this technique to improve air quality prediction accuracy. And the objective also includes validating the proposed method using real world data from Madrid and compare the model's performance with reference models that are temporal graph convolutional network, long short term memory, and gated recurrent unit using evaluation metrics like accuracy, precision, recall, and F1 score. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front-end framework used is Flask, back-end framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of law of work. So the first step is import and required packages. In this step, we will import essential libraries such as NumPy and Pandas for data manipulation and analysis, sklearn for machine learning and data pre-processing, TensorFlow Keras for deep learning, Matplotlib and Seaborn for data visualization. The second step is exploring the dataset. Here, we thoroughly examine the air quality dataset to understand its structure, features, and distribution. This exploratory analysis is crucial for gaining insights into the data's characteristics before further processing. The third step is data processing. So, data processing includes tasks such as using Pandas data frames for efficient manipulation, generating a target variable based on PM10 values, employing Keras data frames for deep learning compatibility, and dropping unnecessary columns to streamline the dataset. The next step is visualization using Seaborn and Matplotlib. So, visualizations using Seaborn and Matplotlib are created to enhance our understanding of the dataset. These graphical representations help identify patterns and relationships, facilitating informed decision making in subsequent stages. The next step is label encoding using label encoder. Here, categorical variables are encoded using the label encoder technique. This step is essential for converting categorical data into a format suitable for machine learning models, particularly neural networks. The next step is feature selection. In this phase, we select the most relevant features for modeling, optimizing computational efficiency, and focusing on variables that contribute significantly to predictive accuracy. The next step is train and test split. In this step, the dataset is split into training and testing sets, a crucial step for assessing model performance. This division allows for training on one subset and validating on another, ensuring robust evaluation. The next step is training and building the model. So, in this step, several deep learning models, including A3T GCN, TGCN, LSTM, and GRU, are trained on the dataset to learn patterns and relationships within the data. So, in the next step, as an extension, we explore additional deep learning and hybrid models. So, hybrid approaches combine predictions from multiple individual models to enhance overall prediction accuracy and robustness. And as an extension, again, a user friendly front end is developed using the Flask framework incorporating user authentication. This front end allows users to input data for testing the trained models. And Flask is utilized to create a backend that interacts with SQLite, ensuring secure sign up and sign in functionalities for user access. After signing in, users provide input, and user inputs are pre-processed to align with model requirements. The trained models are then utilized for predictions based on the user's input. And the final prediction outcomes are displayed through the front end, providing users with intuitive insights derived from the trained models. Now we'll discuss about the algorithms used. So the first algorithm built is A3T GCN, that is Attention Temporal Graph Convolutional Network. So A3T GCN combines graph convolutional networks with attention mechanisms for spatiotemporal prediction. It excels in capturing spatial relationships and temporal dependencies, making it ideal for predicting nitrogen dioxide concentrations in Madrid, where both factors play a crucial role. The next algorithm built is TGCN, that is Temporal Graph Convolutional Network. So TGCN extends graph convolutional networks to handle temporal dynamics, allowing it to capture evolving patterns over time. Its suitability for spatiotemporal prediction tasks makes it valuable for modeling air quality data and predicting nitrogen dioxide concentrations while considering both spatial and temporal dependencies. The next algorithm built is LSTM, that is long short term memory. So, LSTM, a type of recurrent neural network, is adept at modeling sequential data by maintaining a memory cell. Its proficiency in capturing temporal dependencies makes it a fitting choice for predicting nitrogen dioxide concentrations based on the sequential nature of air quality data. And the next one is GRU, that is gated recurrent unit. So GRU, another type of recurrent neural network, simplifies the architecture while retaining effectiveness in capturing temporal dependencies. Its computational efficiency makes it suitable for projects where resources are a consideration, and in the context of the project, it efficiently models temporal dependencies in air quality data for accurate predictions of nitrogen dioxide concentrations. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing accuracies of different algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. Accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is precision scores comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F1 scores comparison graph. In this graph on x-axis I have F1 scores and on y-axis I have algorithm names. F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And this is Madrid dataset file, in which I have the required Madrid dataset with class labels on which we will train the models. And this is the model file which contains algorithm information. This file will be loaded into the project code during runtime to utilize the trained models. This is notebook Jupyter source file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. Now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. Now use the command cd followed by a space and paste the copied path and hit the enter button. So this command will change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. If we are new users, we have to register first. Fill in all these details and click on sign up button to register. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide a credentials, username and password and click on sign in button. So it has redirected us to the classification page. Now we have to fill in all these parameters and click on predict button to get the classifications. So first we'll understand these parameters. So volatile organic compounds, that is VOCs, including Ben, that is benzene, EBE, that is ethyl benzene, MXY, that is M-xylene, PXY, that is p-xylene, and TOL, that is toluene, are emitted from various sources such as vehicle exhaust and industrial processes. These compounds contribute to air pollution and environmental concerns, posing health risks. The next parameter is CO, that is carbon monoxide. It is a colorless, odorless gas produced by incomplete combustion of carbon containing fuels, posing health risks by reducing oxygen carrying capacity in the blood. The next one is NMHC. So it is a group of hydrocarbons excluding methane released from combustion processes contributing to air pollution and atmospheric reactions. The next parameter is NO2, that is nitrogen dioxide. It is a major air pollutant generated from combustion processes, especially in vehicles and power plants, with adverse effects on respiratory health. The next is NOx, that is nitrogen oxides. It is a collective term for nitrogen dioxide and nitrogen oxide produced from combustion processes contributing to air pollution and acid rain formation. The next is OXY, that is oxides of nitrogen. It is the compound formed from the combination of nitrogen and oxygen during combustion, contributing to air pollution and respiratory issues. The next is O3, that is ozone. It is a secondary pollutant formed by chemical reactions involving precursor pollutants with both beneficial and harmful effects depending on its location in the atmosphere. The next parameter is SO2, that is sulfur dioxide. It is a gas produced by burning fossil fuels containing sulfur, contributing to air pollution, acid rain, and respiratory issues. The next one is TCH. It is the total concentration of hydrocarbons, including both methane and non methane hydrocarbons, present in the air. And the last parameter is PM10, that is particulate matter 10. These are the inhalable particles with a diameter of 10 micrometers or smaller, originating from various sources such as vehicle emissions and industrial activities impacting respiratory health. Now we'll fill in all these parameters. Ben would be 0.73, CO is 0.61, EBE would be 0.91, MXY would be 1.60, NMHC would be 0.13, NO2 would be 49.6, NOx would be 51.2, OXY would be 0.87, O3 is 17.09, PXY would be 0.64, SO2 would be 12.68, TCH is 1.43, TOL would be 4.36, and PM10 is 56.45. Now click on Predict button. So here we can see the result, that is air quality is bad based on the input provided. So for the given parameters, the application has predicted it as the air quality is bad. Now click on home link. We'll try again, giving another set of parameters. So this time BEN would be 4.47, CO would be 2.78, EBE is 5.33, MXY would be 13.21, NMHC is 0.45, NO2 would be 131.1, NOx is 459.89, OXY would be 6.25, O3 is 6.42, PXY would be 5.08, SO2 would be 30.12, TCH is 1.78, TOL is 26.20, and PM10 would be 38.42. Now click on Predict button. So here we can see the outcome, that is air quality is good based on the input provided. So similarly, we can give any set of parameters and can get the classifications if the air quality is good or bad. Now click on sign out. So the conclusion here is the project successfully employed advanced models including A3T GCN, TGCN, LSTM and GRU to enhance the accuracy of nitrogen dioxide, that is NO2 concentration predictions in Madrid. The utilization of these models showcases their effectiveness in capturing complex spatiotemporal patterns within air quality data. By considering air quality, meteorological, and traffic data, the project provided comprehensive insights into the factors influencing NO2 concentrations. This holistic approach ensures a more nuanced understanding of the dynamics involved, contributing to informed decision making for pollution control measures. The significance of the project lies in its potential to offer decision makers advanced knowledge of air quality concentrations. The spatio-temporal prediction models serve as valuable tools for government bodies, environmental agencies, and other stakeholders, facilitating the implementation of targeted and effective pollution control measures. And the exploration of various deep learning models and hybrid approaches demonstrates a commitment to optimizing prediction accuracy. By combining predictions from multiple models, the project aims to provide a more robust and reliable tool for forecasting NO2 concentrations, considering the intricacies of air quality dynamics. And the development of a user friendly front end using the Flask framework with user authentication underscores the project's commitment to practicality. The integration of user input processing and model predictions ensures accessibility, allowing individuals to interact with and benefit from the predictive capabilities of the developed models.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.